gathered to hear Dr. Brad Carroll tell us about things he doesn't understand, and he has very nicely condensed that down to only 1 hour. So I'm looking
It was hard.
next week we may not have a talk, so look for the posters. Thanks.
This is actually a talk I've been thinking of giving for a couple years, because every time you go to a meeting, people talk about the sort of things that they already know, and you sit there and you think, my gosh, I sure feel dumb. You know, this is stuff I should understand, I don't. And so I thought, how nice it would be that if I talk about stuff that I don't understand, and, you know, that way we're all here together, because I don't think anybody understands this stuff. And it also makes me bulletproof against people asking questions. And if you ask me a question about anything that's up here, all I have to do is say, I don't understand. So please feel free to ask me any questions you want to, because you'll always get the same answer. So, what I don't understand, and there is a lot I don't understand. There honestly is. And so I know, is this not, I don't know if my little device is working. I can always do this manually. Oh, that doesn't work either. I don't understand why this isn't working. So I'm just going to close it and open it again and see if that works. So let me see, open with, and there we go. Okay. So now let's see if this works. Yes, it does. Okay. There's a lot of things I don't understand. I don't understand about music, body, and desire in medieval culture. I know very little about winning mahjong, Chinese and American. Epigenetics and psychiatry I know nothing about. Short history of the Austro-Hungarian Empire. No, not really. And there's a lot of things in physics I don't know about. You know, I've taught a lot of courses here over the years, but there are some courses that I shouldn't be allowed to teach. I shouldn't be allowed to teach solid state or electronics or optics, or actually computational now, because that's changed a lot since the invention of the abacus, and I haven't kept up the way I should have. But I want to talk about 3 different things I don't understand. And there really are puzzles to me, and there's 3 types. First of all, there's things that probably have answers. And, you know, the physics is clear, but the application of the physics is a little bit controversial and contentious. Okay? Then there are things that may have answers, okay, or may not. Here the physics isn't quite so clear, and the application of the physics is still contentious. And finally, there's things that just may not have answers. And in this, the physics is not clear, and the problem may be significant, and it may have a deep answer if it has one. And so that's what I want to talk about, these 3 things that I don't understand. 3 things among many. And as Dr. Holt mentioned, I've cut this way down so as not to keep you into the next millennium. Okay. So first thing, talk about something that probably has answers, and the physics is clear, but the application is contentious. And this has to do with the good old question of what happens if I have a particle in a box. Okay. Now this is Prince Louis de Broglie. Okay, that's Prince Louis de Broglie that you saw up there. Apparently I can't use this advancer, but there's Prince Louis. Dapper little mustache. He is one of the great founders was one of the great founders of quantum mechanics. He lived until 1987, and he taught us that nature has a wave-particle duality, that particles have wavelengths, and that the wavelength of a particle is just some number called Planck's constant divided by its momentum, its mass times velocity. Okay. Now, that means all particles have a wavelength, but we don't notice our wavelength because h here is tiny, and so we don't notice our own wavelength. It's very tiny. It does become important on atomic scales, and scales of I forget, what is the scale when quantum takes over, Colin? Is that like 10 Fermis or?
Yeah, somewhere in there.
Somewhere around there? Okay. Yeah, something around there. 10 to the minus 10 meters. You can solve this. I'm sorry, that was an inside joke. The wavelength, I can solve this for the velocity of the particle, and the velocity of the particle is Planck's constant, that's a tiny number, divided by the particle's mass times wavelength. So, let's put our particle in the box. The particle is going to go into the box, and so it's somewhere between these two walls. And how can I have a wave in a box? Okay, the only way I can have a wave in a box is the same way a string can vibrate in a box. So here's the fundamental, the first harmonic, second harmonic, third harmonic, fourth harmonic. I can look at these patterns, I can tell what the wavelength is. Here you can see there's a half wavelength that fits between the two walls. And so that means the total wavelength is twice the length of the box, twice the distance between the walls. Here for this, you can see that there's a full wavelength in there, and so the wavelength of this wave is just the length of the box. Here's the third harmonic. You can see that the one wavelength goes from here to here, from there to there. And so the third wavelength is 2/3 the length of the box, and here the fourth wavelength from here to there is half the length of the box. And so I can write those wavelengths as 2L/1, 2L/2, 2L/3, 2L/4. And that means in general, for some pattern, the nth wavelength, where n is 1, 2, 3, 4, and so on, is going to be 2L divided by that n. Twice the length of the box divided by whatever vibration pattern I'm looking at, 1, 2, 3, 4. Now what I can do is I can put that into de Broglie's relationship for the velocity of the particle. Remember what that was from the previous slide. He said that the velocity of the particle is h divided by the particle's mass times divided by its wavelength, h over n lambda. So if I just plug in what those wavelengths are, I get the possible speeds of the particle in the box. Okay. So if n is equal to 1, it moves so fast. If n is equal to 2, it moves twice as fast. If n is equal to 3, it moves 3 times as fast. If n is equal to 4, it moves 4 times as fast, back and forth. Okay? And these are the only speeds the particle can move at. So if I just put a bunch of particles in a box, just take a bunch of particles and floop, put them in a box, they're going to go back and forth. It's a one-dimensional problem. They go back and forth. But the idea is that the speed of the speeds of those that are moving like this, in this pattern, are moving twice as fast as the ones that are in this pattern. These speeds are 3 times what they are here. These speeds are 4 times what they are here. Which means that every time this particle comes back to where it started, all the rest of these come back to where they started, although this one will have gone back and forth twice. This one will have gone back and forth 3 times. This one will have gone back and forth 4 times. But in the time it takes for this particle to go from one wall to the other, all of these particles will be back where they started too. Okay. Now, so far that's okay. And so I can figure out, what is the time for the particle to travel back and forth across the back and forth across the box. And this is just putting into math what I was just telling you about. The time to go back and forth is just 2L, the total length back and forth, divided by the velocity. And you work it out, and it turns out to be this. The idea here is that the n is on the bottom, and so the higher the n is, the less time it takes to go back and forth once. But when the box is filled with random particles, they will go all back to their original positions after this time t1 for ml squared over h. So I think that would be cool to watch happen. These waves moving from one side of the box to the other. So I think that would be just fantastic to do. So, You know, that's pretty easy. How do you do that? Well, heck, if I want to do that, I have to put the particle on one side of the box and let it move across. Okay? So, if I was to do this classically, what I could do is put a particle in a box. It's not a wave here, it's just a particle. And then I would suddenly yank this wall over so the box is twice as big. That puts the particle definitely on this side, and then I would just watch it go back and forth. Okay. Well, I can do the same thing in quantum land, in quantum mechanics. I could start out with this nice wave. This was the easiest way I could have that wave. Remember the n=1 pattern. And so what I'm going to do is that it exists right here, and I'm going to move this wall out suddenly. And then I'm going to watch this move from one side to the other. Okay. Now, there are ugly details. Here are ugly details. Good, you've seen enough. If you know about this, you saw that I did it right. If you don't know, I'm not going to intimidate you. But the idea is that here is my particle in the box. And I want to watch this as it goes back and forth. And so let's do this. So right now, this is where I start out, and suddenly I'm going to yank boom, the wall out. Okay. What do you think you're going to see?
Something you don't expect.
Oh, very good. That is an excellent answer. Okay. Here's what you get. Looks like two ferrets fighting under a sheet.
Brad, what was your resolution?
I went up to about 1 on this. I used the first 99 terms.
Oh, okay. So, okay, 99, you expanded it in a series of about 99
Yes.
assignment. Okay.
Uh-huh. Oh, I'm sorry, Dan. I don't understand. So this just keeps on going. Just when you think it's going to... Look, this is ridiculous. I mean, it really is.
Are you sure it's not 3 ferrets?
Sometimes it looks like 3. Sometimes there's a little baby duck in there. You know? I have this thing about baby ducks. I don't know. It still hasn't gotten back to where it started until now. Oh, that was stupid. Okay. So that's what it looks like. And so I wondered, well, quantum mechanically, what you can do is that this represents, with this wave, this is really psi star psi. This is the probability of finding the particle at a certain location. And so what I can do is I can ask myself, well, where on average is the particle? And I can make a graph of that, where the particle is as this happens.
Brad?
Yes?
So if I'm understanding this right, you ended up in some multiple of 2 pi for time.
Right.
Okay.
Right. I have an energy that goes like e to the I, e energy 1 times n squared times t, and so I let that go through 2 pi.
Okay.
Yeah, at the lowest level. So I've gone through one cycle of what happens to the n=1 wave function.
Okay.
I don't understand. So let's see where the particle is then on average as it moves back and forth. What do you think that's going to look like? Here's what it looks like. It starts here on this side, time goes upwards here. Here's 0 to 100, the particle in the box. And as time goes on, the particle goes from one side to the other side. And so, for some reason I have a hard time finding my cursor. There we go. Okay. And so as this thing moves along, the average value just moves nice and smoothly along this line. You can see now it's all the way over on that side. Now it sort of comes back so it's even. Now it's come over to the left a little bit mostly. And then it's going to zoom over to the other side. Until I'm halfway through my cycle, right there. And then I keep going. And so notice how the average value of x changes, despite the ferrets and the one little baby duck fighting under there. You get this nice smooth behavior for the average position of the particle in the box. And I just find that fascinating. And then I remember, let me stop this. I can do that. There we go. Oh, well, I didn't have to. There it is. Here's what I don't understand. I'm trying to reconcile this with Ehrenfest's theorem, which basically says that expectation values behave in a classical manner. This is just mass times acceleration equals force. So this is Newton's second law. M times A, force times acceleration equals the force, minus the partial derivative of the position with respect to time. And there's no force, right, except when it hits the wall on either side. And I'm trying to reconcile Ehrenfest's theorem with this. And I don't understand. I really don't. I mean, here these little regions are interesting, aren't they? This is where the particle isn't moving for a second. So I got really confused about this. I hope, if you're out there waiting for a punchline when I'm going to reveal how it really works, I'm not. Because I don't know what's going on here. But I did, you get inspiration early in the morning. When you first wake up. And so I had an inspiration yesterday, which was to ask, what if I squeeze that particle into 1/10 of the box and then opened it up? How would this be different? Okay. This part where the particle's at rest stretches out. And the little wiggles are confined to a little bit here, and then a little bit up there. But I still am trying to reconcile it with Ehrenfest. So, in other words, the particle in a box is one of the great inventions of physics. With a particle in a box, you can derive all of the behaviors of an ideal gas. You can figure out what the entropy of an ideal gas is, which you never tell beginning physics students because it has H in it. You don't want to scare them. And, it's a great success. And yet there's a lot, including this, I just don't understand. So if anybody has an idea about how to reconcile this, this strange meandering, although it does have nice symmetries, this strange meandering with a particle hitting the wall.
Brad,
Let me know. Yeah.
I have no insight. What does the histogram of that look like if you were to just count up the number of times it is at a certain value and plot it as a histogram? Would it be a distribution around the center, or what does it look like? You can say I don't know.
I'll vary my answer for you, John. I have no idea. But it's an interesting idea because it does look, on average, I think the particle does appear to be at the center, doesn't it? And I think that becomes more and more severe as I confine the original particle more and more toward the walls. So, that's something I don't understand. That's probably the most arcane thing I don't understand. Yeah?
So, and this question is going to come from me not understanding this either, but
Okay.
In an ideal gas, if you were to simulate this and you were to say everything's compressed, and then in the computer say, I've made a bigger cylinder, model it, you're going to get something that doesn't look really real because you've kind of artificially grown the volume of the box without actually enacting the force on the gas. Does that make sense? You're not, in other words, in real life, you're going to have a gas in there, and you're going to pull it, and the gas is going to react as it goes.
Yes.
So did you do that here, or did you just kind of say,
This was an instantaneous movement of the wall. So
Okay.
the walls never touched the gas. It was an adiabatic
Okay,
process.
okay.
And so it never touched the gas. Yeah. Okay. Here's something else I don't understand. So you're gonna leave here not having learned anything. Okay? I don't understand the radiation by an accelerated charge. Now this is one of my favorite diagrams in all of physics because it shows what happens to the electric field of a charge that initially is at rest at the origin. And here's the electric field lines all pointing toward the origin. Right, the information is traveling outward at the speed of light. And then at the origin, the particle suddenly accelerates and then moves at a constant velocity. So here's the electric field lines pointing toward the charge when it's moving at a constant velocity. And here's the connection of those lines, the electric field lines, from when it was at rest to when it's moving at constant velocity. So the lines going around like this are the more or less transverse electric fields that are associated with radiation. This is one of my favorite pictures. Dr. Schroeder worked with a student, John Metcalf. Was it Metcalf who did that, or was it
Andrew,
who?
Andy.
Andy, yes. Flinders, Andy Flinders, worked with Dr. Schroeder and had a wonderful animation where he could just drag a charge and you would see what happened to the radiation, to the electric field of that charge. And so we understand that. And for those of you who are in my waves class, on the last day of the semester, you're going to probably see this formula, because that's my goal. This is the power that is radiated by an accelerated charge. This is the energy per second the charge gives off. Here's the acceleration. That's all you got to know. I'm not going to. It's an important formula, but if a charge Q has an acceleration A, then this is the energy per second, the power that it gives off. So I could put an electron. You can tell it's an electron because it's a red ball. It's out in space. And I accelerate it with an acceleration equal to 1g. And it's going to give off electromagnetic radiation. Is that okay? Okay. On the other hand, there is Einstein's equivalence principle that says it is impossible to tell. Here's Einstein in a box. A big box with Einstein. Okay? And it's impossible to tell if you are in an elevator accelerating upwards at 1g, or if you're on Earth in a gravitational field of 1g. There is no experiment you can do inside the box to tell you the difference between the situations. But we've just seen that our electron that's accelerating upwards at 1g emits light. So, does an electron at rest in a gravitational field radiate? Which would be what the equivalence principle demands. Or, the other possibility would be, or does a uniformly accelerated charge not radiate? The nice thing about getting stuck on stuff like this is that you can look back in books about it, and you're sort of grateful when you find out other people were stuck on it too. Two of the people that were stuck were Wolfgang Pauli, who always looks like a shark to me, and Richard Feynman, okay, who both very firmly said that a uniformly accelerated charge does not radiate. Okay. Oh, that's interesting. And then the tables started to turn, because people really started to ask, well, what do we mean by a uniformly accelerated charge? Does it radiate? Meaning, does it give off electromagnetic radiation? And uniformly accelerated means that it accelerates uniformly. I'm proud of myself for that one. Okay. Which means that it continues to speed up and speed up and speed up and speed up, and eventually approaches the speed of light and exceeds the speed of light. So to talk about a uniformly accelerated charge is somewhat difficult. And so people have begun to talk about this hyperbolic motion where a particle comes in along the z-axis and then reverses itself. Now there's a bunch of math up here, I'm not going to talk about it. Okay? But it starts out, here's the z-axis, the particle comes in and then heads out. Around the origin in an inertial frame, it has an acceleration equal to 1 Earth gravity, and then it goes back out again. still accelerating smoothly according to these equations that talk about its location on the z-axis, its velocity, and its acceleration. So this is the context in which people have to try to answer this question. And anytime you see something like that, to answer a simple question, you know you're in trouble. So let's see what happens, what they figured out. Okay. What they figured out is that this is science by vote. It's the democratic process instead of actually finding an answer. Right now, most people say that yes, a uniformly accelerating charge does radiate. But it radiates into a place where if you're moving with the charge, you can't see the radiation. Honestly. Okay.
Is that an 80?
Now remember, I'm going to read this to you, but I don't understand this. Well, you find out that a freely falling charge will radiate according to an observer at rest. However, an observer freely falling with the charge would observe it at rest and no radiation at all. To explain this puzzle, we need to recognize that the concept of radiation has no absolute meaning and depends both on the radiation field and the state of motion of the observer. The reason for that is that we do not see a charge where it is at the moment. We see a charge where it was. We have to look back at what is called the retarded time of the position where it was back then when it emitted the light that we see. And so it becomes complicated, and that's why all these motions are thrown in. Okay? We can conclude that co-moving observers have no access to the radiation field of a uniformly accelerated charge. The concept of a horizon emerges naturally in this context. The electromagnetic field generated by a uniformly accelerated charge is observed by a co-moving observer as a purely electrostatic field. And so, if you see an accelerated charge move past you, according to this, it does radiate. If you move along with it, it radiates into a place you can't see, so effectively it doesn't. Please note the title.
So this isn't really any different from just a non-accelerating charge making a magnetic field or not making a magnetic field, whether you're moving with it or not. So if you walk with an electron that's moving, you don't see a magnetic field, but the person standing next to you watching it go by sees a magnetic field.
Well, that's because of a relativistic transformation of electric fields into magnetic fields and magnetic fields into electric fields.
Yeah,
But that's not what's behind this.
Okay.
This has to do fundamentally with what radiation means and how it works for accelerated charges to radiate.
Okay, well, I would argue that your earlier statement on the electron moving along is a definition of radiation.
But into what region of space does it radiate? And the argument, remember those awful equations I told you I wasn't going to talk about. Okay. Notice that this says that if the particle is here, it says, I'm shining the laser into my palm. That's the depth of my ignorance. Notice it says that where you are is always going to be less than CT squared. Where you are is always going to be less than CT squared because this is positive. But the radiation, it turns out, goes into a region that exceeds CT squared. And so you can't see it. It's in a region of space that is not accessible to you. At least that is what this guy says. This was in 2006. You can look it up in the American Journal of Physics. I understand that one of us has an insight into the processes in that journal.
This paper was published under the previous administration.
But then in 2008, here comes this book out by Springer, which disagrees with it. So I'm so confused. So that's the second thing. But I think it's fascinating to know that the question of whether a uniformly accelerated charge emits electromagnetic radiation or not is unsolved. That to me is really surprising. Yeah.
So by electromagnetic radiation, do you mean energy being carried away or field?
Oh gosh, then there's a question of where the energy comes from.
Okay.
And that's very good because there's radiation reaction forces. And so there's a question, does the light that's radiated away come from the electron's own charge, its own energy, and I don't know. It is not known.
Brad,
Yeah.
how does this tie in with an atom being at rest and radiating by quantum processes?
This is purely classical, so there's no quantum in this.
Okay.
So this is purely Maxwell's equations.
If somehow you sneak quantum into it and solve the problem?
If by you mean me, the answer is no. If somebody might be able to, but it's still a matter of contention after almost 100 years. Okay. So here's things that don't have answers. Okay. The physics isn't clear, and the problem may be significant and have a deep answer. And this is cause and effect. So, what do I mean by cause and effect? John, would you care to read this out for us?
This is an outrage! How dare they? Don't they realize that I collaborate with people outside of Weber State, and this will be much more difficult for my collaborative and very important efforts? I'm paraphrasing.
Okay. So that is the cause. The effect is the look on Dr. Ingolfield's face. First there's a cause, which actually does something. And then there's a response. Okay. So, cause and effect. Okay. So, how about cause and effect? Why am I worried about that? I mean, you could go into the philosophy of cause and effect and determinism and a whole bunch of stuff. No, I'm confused on a much more basic level. It's good to be confused on a basic level. Because then, you're not just confused about words, you're confused maybe about something that's actually meaningful. But here's cause and effect. This is the well-known electron double slit experiment. And you've all seen this, you know how it works. There's an electron source here that shoots electrons out, and the electrons go through two slits. They hit a screen where there's a detector that can measure how many electrons are hitting, and you can count the electrons that hit. Okay. Now, if only slit 1 is open, the distribution of particles that go through slit 1 on the screen looks like this. That is, the particles pile up behind slit 1. If only slit 2 is open, then the particles pile up between slit 1 and behind slit 2, I'm sorry. The particles pile up behind slit 2 because only slit 2 is open. If both slits are open, you get this interference pattern. Because particles are waves, and when the waves go through both slits, they form an interference pattern. You can do this. In fact, we do a variation of this in our senior lab, where one particle at a time goes through the slits. And you still get the interference pattern, which means that each particle goes through both slits. I'm okay with that. I don't understand that, but nobody does, and that's okay. And so here's the deal, okay? It's almost off the screen here, but if both slits are open, then here's how I would describe the wave. The total wave, which is this Greek psi thing, the total wave is equal to the sum of the waves going through slit 1 and the waves going through slit 2. So this is what it is if both slits are open. However, if slit 1 is open, then the waves are only described by particles going through slit 1. If only slit 2 is open, then the wave is described by particles only going through slit 2. But again, if both are open, then here's the total. So you think, well, this is stupid. You can't have one electron going through both waves, or through both slits. It's ridiculous to think an electron could be through both slits at the same time. So you look for them. And so you set up these little detectors behind the slits. Okay? And sure enough, you only see an electron through slit 1 or slit 2. And when you do that, this interference pattern disappears. And you get simply the sum total of these two curves right here. If you don't look, the electron goes through both slits and you get an interference pattern. If you do look, the electrons behave and they either go through slit 1 or slit 2. Now, what that means, I mean, there's no theory here. I've just described an experiment. And so what this means is that when you look, you do something to the wave function. You do something to this wave that takes it from this wave 1, slit 1 plus slit 2 wave, and then you collapse that wave function, to use the technical term. You collapse that wave into pure slit 1 or pure slit 2. So you do something, cause and effect. You use a detector. The effect is that the wave function collapses. Okay? So it's cause and effect. You look at the wave function collapses into either pure slit 1 or slit 2. Now, do I have to look at it personally? Is consciousness involved? Or is just, a detector registering a signal enough? Doesn't matter, it's still cause and effect. And I'm not going to get into that debate, although I have opinions on it. But that's stuff I'm willing to talk about, even though I don't understand it, which, come to think of it, is what this talk is about. So let me know. But the idea is that in looking, there it is. This is angle sensitive, so sometimes if I shake it, it works, and sometimes it doesn't. But the idea is that I have interacted with the particle, and that has caused the wave function to collapse. Okay, good. Same thing with the famous Schrodinger's cat. Right, if I put a cat inside a box, and there's a little radioactive substance here, which may or may not decay in the next hour with a 50% probability. If it decays, then a hammer's dropped, releasing poison, which kills the cat. If it doesn't decay, the hammer stays up and the cat lives. And the idea is that if I don't look, what's the wave function? The wave that describes the cat is composed with equal parts of a live cat and a dead cat. But when I look, that's a cause, and the effect is that it collapses the wave function to produce either a live cat or a dead cat. Okay. That's fine too. So, cause and effect. Can relativity change the order of cause and effect? Good, for instance, Colin get this look on his face, and then John, hold forth.
That happens all the time.
It's really not your fault, is it?
No.
It's Dr. Inglefield who does this. Well, I just want to show you something rapidly and hope that this works. But I want to switch over to a little animation that just talks about how relativity works with the order of things. And what I have is a train car here. It's a box car. And there's a little light bulb in the center of the box car. The light bulb emits a burst of light. The burst of light spreads out. There are light sensors on the doors, and the doors open when the light hits them. Okay? So there's a light in the center of the box. The light bulb goes off. The light spreads out. The doors open. So what I want to do is I want to look at this, first of all, from the point of view of somebody traveling on the train. Okay? And they're going to stay right there because they don't think they're moving. They're going to look outside, see the tree moving past them. But you'll see the light bulb go off, and you'll see the doors open. So here we go. Light bulb goes off, doors open. Both doors open at the same time. Is that not amazing? Eventually? Let's see it again. There it goes. Light bulb goes off, doors open at the same time. Great sound effects. Okay. Now let's do it from the point of view of people on the ground. Okay. So here are two observers. They're now at rest. They're going to watch the train car going by. The light bulb's going to go off. Let's see what they describe. Boom, light bulb goes off. Back door opens first. Front door opens. right? And look, I mean, here's where the light bulb went off. The speed of light is the same in all directions. So if they're on the ground, they see one door open before the other door. I'll run it again. Here runs along, light bulb goes off, back door opens, front door opens. So whether, if I have two events, two happenings that occur, when I say it happens at the same time, if there's somebody moving relative to me, they will measure that one happened before the other. And who's right? The answer is yes. Because they both are, because otherwise you can tell who's really moving. Dr. Armstrong.
So, but the doors open because they get hit by the light. It's not that the doors open because one door opened and the other door opened. So the cause is the same in both cases. The light hit the door.
Yes.
It's just so that you haven't violated cause and effect. You've just changed the
That's
simultaneous.
right. I have not violated cause and effect here. All I've done is shown that.
There was
Right,
a
I
cause,
just-
but there wasn't an effect.
All I've shown is that in one frame of reference, two things happen at the same time. From a moving observer will not see them at the same time. And so you might wonder, well, gosh, going back to my laptop here, if it will let me, and if it will let me continue going here, running auto setup. I have no idea what that meant. Okay. So, when can you reverse cause and effect? Can you? And so here's the deal. We have two events here. Event 1 happens at location x1 at a time t1. That's the earlier event. Here's a later event. It happens at another location x2 at a time t2. Here's how to tell if you can reverse the order of the events. When event 1 happens, you shine a light out. You shine a flashlight. And it tries to get to event 2 before event 2 occurs. Okay. Event 1 happens at the same time the light leaves. That light tries to get to event 2 before event 2 occurs. Okay? So, if a light beam starting at event 1 cannot reach the location of event 2 before event 2 happens, then event 1 could not have caused event 2. Right? Because there's no way information from event 1 could have reached event 2, so it couldn't have caused it. Okay. In that case, another observer moving relative to our frame of reference could see event 2 happen before event 1. So, if a light beam can't go between the two events, then another observer could see the events occur in the other order. You can get that out of the Lorentz transformations pretty easily. And so, here's a spaceship, Captain Proton, who sees event 2 happen first instead of event 1, who's moving in that direction. Let me tell you how weird this is. Here's the Andromeda Galaxy. It's 2.5 million light years away from Earth. On that galaxy, somewhere down here, there is a planet inhabited by baby ducks. Its sun goes supernova, destroying a planet filled with cute baby ducks. At that time, a ray of light leaves this doomed planet and goes to Earth. And a nanosecond before it reaches me, I slip on a banana peel, an equally tragic event. That light has been traveling for 2.5 million years. But I slip on the banana just before the light reaches me. That means a person moving in another reference frame would measure my slipping on the banana before the ducks were destroyed by a supernova. That's how weird these are. That's how weird this is.
Yes.
So, why is this important? Hey, why am I bringing it up? Okay. So here's what I don't understand. Okay. This is the famous Einstein-Podolsky-Rosen experiment. And here's what's going on. There's two observers, I'll call them Alice and Bob. Okay? And there's a machine in the middle of them. And it emits, here's an electron, here is a positron, positive electron. Okay? And it emits them in opposite directions. Okay? And the two are united in such a way that if Alice, okay, what's the difference between these two? These are both an electron, these are both a positron, a positive electron. The only difference is which way they're spinning. The green one means they're spinning around this way. The red means it's spinning around in the opposite direction. You can talk about those as spin up and spin down. And there's a correlation. There's a correlation here. I'm going to turn another bank of lights off because I want you to be able to see the bars. Can you see the, maybe you can see the bars down here. It just shows what Alice and Bob measure. And it turns out that if Alice measures spin up on her electron, Bob measures spin down on his proton. Always. So before the measurement, you're in a combination of the states, where it could be either combination. But once a measurement is made, the wave function collapses. And it's either spin up here, spin down for Bob, or spin down for Alice and spin up for Bob. Right? But before the measurements happen, it's both. Now what's weird about these is that you can have Alice and Bob arbitrarily far apart. So far apart that let's say that Bob makes a measurement. Okay? That collapses the wave function. And then later Alice makes a measurement. Okay? Bob's measurement collapses the wave function, and later Alice makes her measurement, and sure enough, the spins are always oppositely directed. Okay? But if they're so far apart that if Bob shines a ray of light that doesn't reach Alice, that means I can find another frame of reference in which Alice makes her measurement first, right? And collapses the wave function. And then Bob's measurement is simply confirmation of Alice's measurement. This is troubling to me. And it's troubling. Whoops, I'm sorry. It's troubling because depending on the motion of the observer, either Alice made the first measurement and caused the wave function to collapse, or Bob made the first measurement and caused the wave function to collapse. So apparently, if causing the wave function to collapse is a cause and effect thing, then yes, you can reverse. In other words, who causes something can depend upon the motion of an observer. And I really don't understand that. So, can the order of cause and effect be reversed? I don't know. Or is the cause of a wave function's collapse inherently non-local in both space and time? And I don't know that either. I'm not even sure what those words mean. But that's yeah. John?
So have we ever been able to actually send information this way?
No, you cannot send information this way because you're... Good question, because you're thinking, well, gosh, if we could just encode these things, and, if Alice could determine, decide whether to measure spin up or spin down, and no, Bob's going to measure the opposite, she could measure stuff that would send a message to Bob. But it's strictly a 50-50 chance what she gets. And so there's no chance of encoding information and sending it faster than light. So you can't, so this doesn't explain ESP or something like that. That's explained by other things that we'll talk about.
So Brad, so when you say non-local, you're basically meaning that the wave function collapse is not governed by cause and effect. So, I mean, is that what you mean by that?
I don't know. But whatever it is, it seems to doesn't mean that what causes the wave function to collapse isn't something that Bob does right there,
Right.
or Alice does right there, at this place in time, at that place in time.
That almost makes me feel better about it. No, because it's always bothered me that there would be this Like I can do this here and that can change over there and you can
Yeah.
flip it around. But if you effectively can't tell, or
Yeah.
you get a different answer depending on how you fly through and watch, that almost makes it more acceptable somehow. That doesn't make it
John,
more
I don't understand what you're saying.
There you go.
But this is what I want to, this is how I feel about these. But there's a lot of physics. I mean, when you take classes and you go through being a physics major or you learn about stuff, you think, oh my gosh, there's nothing left. There's so much that is not understood. And I just wanted to share a little bit of what I don't understand, but I think it's interesting anyway. So, thank you. Oh my gosh, okay. I'm going to take a student question first, and then I'll take Dr. Schroeder's question.
Which of those signs would you say best describes you?
I would say the, oh gosh, I'm disoriented. I don't know, I'm really perplexed, and it's not clear to me whether I'm lost, confused, or bewildered. So it's not clear. Dr. Schroeder.
What does it mean to understand?
No, you're right, because I think what Dr.
It was a question.
Okay. No. I think you're asking, physicists use quantum mechanics all the time, and they're perfectly happy doing it, even though there are some deep problems with it. So to understand something, gee. I don't know. I mean, there are things you don't understand and then you do. I think when it fits coherently within other views that you hold, so that it fits seamlessly into your other understanding of the subject. That's what it means for me to understand. Or that it explores new territory. I mean, if it only did that, then you couldn't make any progress. Or that you observe something new and there is a coherent theory that survives tests, roughly.
In the double slit experiment,
Uh-huh.
how do we know without measuring the electron, how do we know that it will go through both slits?
Because an interference pattern can only be produced by waves and never by particles. And it can only be produced by waves that go through two slits from two sources. That's the only time you can get interference patterns.
So how do we get the interference? How do we measure that there actually is?
Oh, because when we measure it, we notice that there is a place where the electrons are, then aren't, then are, then aren't, then are, then aren't. If it's from two speakers, it would be where the speakers are loud, soft, loud, soft, loud, soft. Yeah.
Can you go back to the picture of Einstein in the box?
Einstein in a box?
Yes, please.
Oh, you mean the that one?
Yeah, that one.
Einstein in a box. I was so pleased to see Dr. Armstrong's comment this one. Yes.
So if you're an adiabatically expand that box 10 times its size, how would you think Einstein's going to do that box?
Like two angry ferrets with wild hair and no socks wrestling undershirts. Go on.
Could you go back to that train with the light and the two doors?
Yeah. It's right here. There it is.
Okay, yeah, go back one or two before that.
One or two before that? Oh, so, okay, so on the laptop. And back a couple, so. Oh, wait.
Still the train.
Huh?
Still the train with the door.
Oh, that's somewhere in the animation. So,
Okay.
yeah.
Okay, so suppose you have the light leave the source, and presumably if you're riding along with the train, it's going to hit both doors at the same time.
Right.
But suppose you have the light go out one door, and somebody on the ground was going to see the light hit one door before it hits the other door. So suppose they have the door open, as the light hits it, lets it go out, and the other door is closed when the light hits that, so the light gets out one door, not the other door. Now, you can't say that one observer is going to see the light go out one door, not the other, and the other is going to see the light go out both doors. You can't very well say that, can you?
All that can be resolved with simultaneity arguments. It's a variation of the pole in the barn argument.
Yeah, that's right. Okay.
Yeah. Which you'll find out about someday. Yeah.
So
Someone remarked about philosophers, it may have been Berkeley, I'm not sure, but they raise a dust and then they complain because they can't see. And I just wonder if you find your talk or your issues here a cut above that criticism, or is it the same?
Let me be unkind to philosophers for a second. Not because I believe this, but you can have arguments about words or arguments about substance. And I hope what I presented today was arguments about substance and not words. If you get into arguments about first causes and type 2 or type 3 sort of experiences of time with McTaggart and all sorts of things, then maybe you're talking about words. But I hope this was more about substance than words. John?
I'm going to stick up for philosophy.
Good, please do.
Here's a possible way of looking at it. We are hardwired with a way of looking at the world and our experiences through evolution, maybe. Of seeing one event always, the first event being the cause, the second one being the effect.
Yes.
When you start fooling around with experiments like this, which doesn't fit with our experiences in the last 50,000 years, which developed our cause and effect in the first sense, of course we're going to be confused because it doesn't fit with the pattern that we're hardwired to account for.
I think that I would not be surprised if cause and effect means something different than our current understanding of it is. And it's going to have to be enlarged to encompass something like this. So I think you agree with our own conception of cause and effect is failing and is inadequate because we don't really understand what the situation is.
It could be,
Yeah.
So any last questions from a student? Then I think we should let people go if they need to get somewhere.
Yeah.
Otherwise, feel free to keep